Wow, week 23, Pure Maths 3 maintenance. Let's take a look at this first question here. I've got this polynomial with a and b constants. It's called px. We know that it's divisible by this. And we've got to find the values of a and b. Alright, so probably what I'm going to do here is I'm going to start by dividing the polynomial by x squared minus x plus 2. And we've got 4x to the 4. Oh, hold up, it's a bit messy. 4x to the 4. That's just my 3-year-old throwing a tantrum in the background. Seems to be her favourite response to her brothers and sisters at the moment. Alright, there we go. So, well, obviously we're going to multiply by 4x squared for the first one. So 4x squared, this will give me 4x to the power of 4. Minus 4x cubed plus 8x squared. And if we subtract that all, we're going to get 0 here, 4x cubed here, and this will be a minus 8 x squared. And then we'll just pull this 11x down at this point, plus 11x. And then I'm going to, obviously I need to multiply by 4x, I think, yep. So we get 4x cubed again, minus 4x squared, plus 8x. Now what we'll get here, we'll get 0, we'll get a minus 8, so I think it'll be a plus, a minus 4. So it'll be a minus 4 x squared plus 3x, and then I'll bring this b down, plus b. The last step here is we're going to times it by a minus 4. And this will give us a minus 4 into x squared minus a bracket a minus 4x plus 2a minus 8. And that should, if that is indeed if x squared minus x plus 2 is a factor, then we know that this is all going to cancel out. So we can say there are two things. I guess the first thing, we know that 3 minus a minus 4 minus minus. Oh, I forgot this minus here, so minus minus. It should be equal to 0. So 3 plus a minus 4 equals 0. So a minus 1 equals 0. So a should be equal to 1. And then the second thing that we know is this bit here. b minus 2a minus 8 should be equal to 0. So b minus, and we know that a is 1, so 2a is 2, take away 8 is negative 6, equals 0, so b is equal to negative 6. Now, when a and b have these values, we've got to find the real roots of the equation. So here's our equation, 4x squared plus x squared plus 11x minus 6. And that means that we also now know this factor here, what this is. So we can write this as 4x squared plus 4x minus 3. So that's a factor. Okay, so 4x squared plus 4x minus 3 must also be a factor. So we could, so if it's a factor, we can set it equal to 0. And I think we're going to go 2x minus 1, 2x plus 3 equals 0. So the roots are going to be 1/2 or negative 2/3. Now, I know that there are no real roots with this equation here, because if you just go b squared minus 4ac, you get minus 1 squared minus 4 times 1 times 2, which is 1 minus 8, which is negative 7. So therefore no roots, no real roots there. So the only real roots must come from this other factor that we found out in part 1, and those are the roots. Okay, hope that makes sense. Let's move on. Now, it's given that z is equal to ln y plus 2 minus ln y plus 1, express y in terms of z. Okay, so I'm going to say, whoops, maybe we went right with the highlighter. I'm going to say ln base e z equals ln, and I'm going to use my log rules to write it as y plus 2 over y plus 1, and therefore e to the z, sorry that's a z not a 2, e to the z, equals y plus 2 over y plus 1. And then I guess I can rewrite that as e to the z into y plus e to the z equals y plus 2. I'm going to go e to the z minus 2 equals y minus e to the z y. I'm going to factorize at this point, so I'm going to have y into 1 minus e to the z equals e to the z minus 2. And so I get y is equal to e to the z minus 2. That's a z, not a 2. Over 1 minus e to the z. And we're done. That's quite easy, that one. The next one, what are we trying to do? This is our equation, and we express it as a quadratic equation in tan theta. So we're going to be using double angle rule, you can clearly see because of this bit here. So because it's cotangent, that's like 1 over tan theta. So I'll write this as 1 over tan 2 theta equals 1 plus tan theta. And then I'm going to go 1 equals, and then I'm going to go tan 2 theta bracket 1 plus tan theta. Now I'm going to use my double angle rule, so I've got my formula sheet that can help me with this if I've forgotten, but it should be 2 tan theta over 1 minus tan squared theta. And that's all into 1 plus tan theta. So probably at this point I'll times both sides by 1 minus tan squared theta. So on the left hand side I get 1 minus tan squared theta equals, and then I have 2 tan theta into 1 plus tan theta. And so I get 1 minus, tan squared theta that's a square, that there. Just fix that up, it looks a bit dodgy, doesn't it? Equals 2 tan theta plus 2 tan squared theta. Now I'm going to bring everything across to the right hand side. So we get 3 tan squared theta plus 2 tan theta minus 1. Now I'm going to factorize at this point. So I guess we can go 3 tan theta bracket tan theta bracket equals 0 plus 1 minus 1. So we get tan theta equals 1/3 or negative 1. Therefore theta is equal to inverse tan of 1/3 or inverse tan of minus 1. Now we're looking between 0 and 180. So we've got 1 here, this is 90 here, this is 180 here, and we've got 1 here. So I'm getting 18.4 for my first one, and 135 degrees, of course, for my second one. Okay, well, we're moving on to differentiation here. And I guess you guys can see that we're going to use the quotient rule. So we'll say u equals sine x, and therefore du dx is equal to cosine x. And we've got v equals 1 plus cos x, and so dv dx equals negative sine x. Okay, we use the quotient rule at this point. So dy dx is equal to u, so sine x. Wait, sorry, wrong one. V. So it'll be 1 plus cos x into cos x, so du dx, minus, and then we go u, which of course is sine x, and that will be into dv dx, so that's minus sine x, and this is all over v squared, so it's 1 plus cos x all squared. And what do we end up getting? We get 1, so we get cosine x plus cos squared x plus sine squared x all over 1 plus cos x all squared. Now I have to show that well, what does this end up being? I can simplify, because cos squared x plus sine squared x on the numerator there is just 1, so I end up with cos x plus 1 all over 1 plus cos x squared. Oh, and you can see I can cancel one of those down, so I get 1 over 1 plus cosine x. Now if you think about the cosine graph, and we're dealing with between minus pi and pi, so this is pi here, this is minus pi here. You can see that 1 plus cosine x is positive for all values between minus pi and pi. Therefore, dy dx is positive for minus pi minus x. Sorry, is less than x is less than pi Okay, alright, nicely done. Okay, so now we're using the old substitution. Okie dokie. Whoa, oh, excuse me, I'm tired. If u is equal to x, square root x, then we can say the du dx is equal to half 1 over 2 square root x, okay? And we can rearrange this and say 2 square root x du equals dx. And we can rewrite that as 2u du equals dx as well. Now, with these ones, it's always a good idea to get some method marks by looking at your limits and substituting them in. So x equals 4, u equals 2, x equals 1, u equals 1. Okay, cool. Now, what else can we say here? Alright, so we can say I equals to 1, and then on the top we can say, well, that's u minus 1. On the bottom we can go 2, and I guess that x is, so I guess we can say u squared equals x, can't we? So we can go 2 bracket u squared plus u, and then we can replace the dx with 2u, so times 2u du, so we can replace the dx with that. Now, what you can see is we can actually factorize that a bit. So on the top we still have this u minus 1. We take the 2u and then we'll have u plus 1 here. And then we've got times 2u du. And you can see that cancels out that, which leaves us with exactly what we want to prove. U minus 1 all over u plus 1 du. And now we've got to show what I equals, hence, so we're using that integration there. So when I integrate this, what could I do here? I would probably then write this as yeah. Oh, okay. What we could do is we could go u plus 1 minus 2 over u plus 1. Now you might be thinking, what in the blue blazes is he doing here? So plus 1 minus 2 is still this minus 1, but what this enables us to do is then rewrite it like this as two fractions. So u plus 1 over u plus 1 minus 2 over u plus 1 all du. Now, then we're going like this. 1 minus 2 over u plus 1 du. Now, this makes it a lot easier for us to, obviously, to integrate. So we're going to get u. Now, this is minus 2 ln u plus 1. And then we've got our limits of 2 and 1. So this will give us 2 minus 2 ln 3 minus, and then we put in 1 minus 2 ln 2. So we get 2 minus 1, which is 1, and then we get plus 2 ln 2 minus 2 ln 3, which is equal to 1 plus ln 4. minus ln 9, which is equal to 1 plus ln 4/9. And we're done. So there we go. Just remember all your log rules to help you there. Okay, the old partial fractions question. I'm going to have a go at one of those. Okay, so this can be rewritten as a over x plus 2 plus bx plus c over x squared plus 4. So be familiar with the different types of partial fractions you're using here. And alright, so I'm just going to say, well, therefore a into x squared plus 4 plus bx into x plus 2 plus c into x plus 2 is equal to the numerator of 3x squared plus x plus 6. And we can say let x equal -2, and then we're going to get -2 squared for 8. So we get 8a is equal to what does that give us? 16? I think it's 16 on the other side. 3, 4, 12, 18. Yeah. So a is equal to 2. Then I'm going to let x equal to 0. And so we get 4 times a, which is 8. B drops out, plus 2c equals 6. So I think c is therefore equal to -1. And then equate the coefficients. Now, looking at the coefficients, there's only 2 ways that we can get an x squared term. It's obviously this one times this one, and this one times this one. So if a is 2, and we need 3x squared here, so clearly that b must be equal to 1. So here we go. This is what we've got. We've got 2 over x plus 2 plus x minus 1 over x squared plus 4. There it is. Hence, we're now trying to obtain the expansion of fx in ascending powers of x up into including the term x squared. So I'll first take this one here. This one. That's what we're taking first. Now I'm going to rewrite that like this. 2 times, oh sorry, that should be to the -1. 2 to the -1 into 1 plus x over 2. So I've divided out that 2 to the -1. And you can see that we're going to end up with 1 plus x over 2 to the power of -1. Now when I expand this, I get 1 minus x over 2, going up to x squared term, plus -1 times -2, all over 2 factorial, into x over 2 squared. And this simplifies to 1 minus x over 2, and that's 2 over 2, which is so x squared over 4. Now, the next one we can rewrite, so this green one here, we can write this as x minus 1 bracket x squared plus 4 to the -1. So it's x minus 1 times, I'm taking out that 4, so it'll be 4 to the -1, into 1 plus x squared over 4 all to the -1. I just flipped the order around in that bracket. Now, so we're going to get 1/4 into x minus 1, and then I'll expand this now. So we get 1 minus x squared over 4. And actually, when you think about it, I don't think we need to go any further because we're only going up to the x squared term. And so we get 1/4 into, we get -1 as our lowest term, so that's that one times that one. Then we need our x term, so the x term would be plus x, and then the next term would be positive x squared over 4. And then I'm just going to times everything by a quarter. So I should have negative 1/4 plus 1/4 x plus x squared over 16. And now I can work out the total. These things, if you look up here, are added. So I'm just going to add these two together. So 1 take away a quarter is 3/4. Minus a half plus a quarter is minus x over 4. And then the last one, I can change both of them into 16ths, so I should get 5 16ths x squared. Doing well, doing well. Okay, now we're into our vectors question. I don't think this is a past exam question. I think I might have got this from a textbook or something. The line L has a vector equation R equals I plus 2j plus k plus lambda 2I minus j. Okay, blah, blah, blah. Position vectors are the 2 points of the line whose distance from the origin is 10. Okay, so in other words, I'm going to rewrite the line like this. I'm going to go, the x point is going to be 1 plus 2 lambda. The y is going to be 2 minus lambda. And the z is going to be 1 plus lambda. Now, if the origin is square root 10, I just need to square all of this. So it's going to be this 1 plus 2 lambda squared, and then take the square root of it. Plus 2 minus lambda squared plus 1 plus lambda squared. So what we're going to get is 1 plus 4 lambda plus 4 lambda squared plus 4 minus 4 lambda plus lambda squared plus 1 plus 2 lambda plus lambda squared. Adding all our squares, we get 4, 5, 6. I think 6 lambda squared. Adding all the other ones, I think we get 2 lambda. And then adding all of the non-lambda terms, I'm getting, I think, 1 plus 4 plus 1. Is that 6 plus 6? Now, excuse me. Actually, I could make this equal to 10 because it's like Pythagoras theorem, isn't it? So if the distance is square root 10, then the square of that is 10. So I'll make this equal to 10. Then I can actually solve it, can't I? That's what I need to do. Plus 2 lambda, take that away, get negative 4 equals to 0. I'm going to divide that by 2. And I guess I'm going to go 3 lambda, bracket, 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 equals 0, lambda, okay, plus 1 minus 2. And so we get lambda equals 2/3 or negative 1. Now, if that's the case, we've got to find the position vectors of the 2 points on the line. Okay, so one point is going to be I plus 2j plus k plus, and then we go 2/3 into 2i minus j plus k. And that gives us, when we add it all together, we get 4/3. So 7/3 I. And then we're going to get 6, take away 2/3. So I think it should be 4/3 j. So plus 4/3 j. And then we've got 1 take away 1 plus 2/3. So it should be 5/3 k. And that's the first one. Now the second one would be if we have I plus, oh bother, 2j plus k minus 1 into 2I minus j plus k. And so we get negative I, 2, so plus 3j, and 1 take away 1 is 0. So yeah, that would be our second one. Now we're on to the last question. Ugh, differential equations, our favourite. Joy. What a joy to behold. Okay, what have we got? We've got a variable point P with coordinates x, y, and point N, which is the foot of the perpendicular from P to the x-axis. Beautiful. P moves on the curve such that for all x is greater than or equal to 0, the gradient of the curve is equal to the value of the area of the triangle OPN, where the okay. Ugh. Okay. The gradient of the curve, so dy dx is equal to the area of the triangle OPN. Okay. Half base times height, so half the x value times the y value. Is that it, isn't it? Yeah. The gradient of the curve is equal in value, so the gradient dy dx, to the area of the triangle OPN. Okay, yeah, no, I think we're good. Well, that wasn't actually that bad. The point with coordinates O2 lies on the curve. Solve the differential equation to obtain the equation of the curve. Okay, so we're going to rewrite it as dy is equal to 1/2 xy dx. Then I can write it as 1 over y dy equals half x dx. Now we can then at this point integrate both sides. So we should get ln y equals 1/4 x squared plus c. Now we've got some parameters here which we can chuck in. So ln2 equals 1/4 times 0 squared, so c. Okay, so that's what c is. And we've got our equation was ln y equals 1/4 x squared plus ln2. And what we have to do is get everything in terms of y in terms of x. So my first step is I've got to write this as ln of e to the 1/4 x squared, there's a quarter there, plus ln2, and then I can write that as ln y equals ln 2e to the 1/4 x squared. Now, because I've got to the situation, remember, ln blah equals ln blah, I can get rid of my ln, so I've got y is equal to 2e to the 1/4, bother, why does it always do that? 1/4 x squared. And that's it. That's our answer. That was actually really easy. Okay, well, I hope that makes sense. Let me know if you've got any questions, and take care.